Today I'm going to talk about the top mistakes that I see the designers of pile-supported bridge projects make over and over again. And we see this based on our practice of performing construction phase pile testing. I'll tell you what I'm seeing as a result of our work and what I think is causing these installation problems. Generically, what we're seeing is that many consultants simply are not coming up with realistic piling designs, or they fail to consider the overall constructability of their design. What we're seeing is that piles that are way longer than they thought they were going to be, or way shorter than they thought they were going to be, piles that are too hard to drive, or piles that have impractical sizes, maybe way too big relative to what area contractors have for typical hammers and cranes for the installation. One of the main reasons this seems to be happening is that engineers designing the pile may never have seen what it takes to install them. As a result, they have not internalized what's typically done in the area and what, say, typical pile section types would be, typical sizes, typical lengths for a given capacity. Part of this has to do with the siloed nature of the industry. You know, you have the owner, the designer, the contractor, and typically a PDA testing consultant or someone who's going to perform the construction phase dynamic pile testing as part of the verification requirements for the pile installation. Many designers increasingly don't have access to confer with more experienced staff in their organizations. This could be due to retirement or just high turnover. Also, many designers never hear about the results of how the installation went for their pile design. We see instances where the same designers have piles that run long on job after job for bridges that are in close proximity. In fact, I've encountered designers where I mentioned that, hey, I tested piling for one of your bridges this morning, and they never asked me how it went. I was kind of shocked. To me, this is like being an engineer who designs rockets for space exploration, but who's never seen a launch or even heard how the launch went for a craft that they designed. To address the gaps in experience and institutional knowledge for past piling projects, my company, Foundation Testing and Consulting, created a relational database with interactive dashboards and plots that we call PileTrack, and we offer this on a subscription basis. Here's a link to a video describing this application if you want to check it out. But getting back to the mistakes that we see that lead to problems for pile installation during construction include a whole list, and this isn't prioritized, but just want to hit the main issues that we're seeing. A lot of it goes back to the subsurface investigation, and not so much the investigation itself, but the decisions that were made to rely on that information and how they're relying on that information. So for example, we see projects where the subsurface borings don't go to the full anticipated pile tip elevation, or have pile lengths that correspond to the exact bedrock contact for one boring for several substructures in that area. And they're not considering the fact that there's variability across the site in terms of variation in the contact elevation for the bedrock or variation in the degree of weathering. So we see instances where the piling is designed to stop exactly at that depth. We recently did a job last week, as a matter of fact, where there was one boring for the entire bridge, and the boring was 150 feet away from the nearest substructure. And the boring went to, I think, roughly 30 feet below grade, and that was the exact pile tip elevation. So they didn't account for any variability between, say, their boring location and their actual substructure. Had the boring been at the substructure location, they didn't account for variability on the other side of the bridge or even along the line of the substructure. Another instance that we see time and again are unrealistically high required penetration depths in bedrock. Several years ago, I had a project that had HP 14 by 117 pile, not exactly a cheap pile section, by the way. And their planned pile lengths were based on the assumption or the plan that the pile would go 50 feet into bedrock. I mean, that's impossible. If the designer had been at all familiar with typical pile installation depths in this same type of bedrock formation, they never would have specified 50 foot of penetration to come up with their pile order lengths. I saw this on the plans, and we were just performing the construction phase PDA testing, but we were notified early enough in the job that I told the contractor, hey, I wouldn't order these plan lengths of piling. There's no way you're going to go 50 feet into the bedrock. Based on my experience, you're going to go 12. And so they ordered significantly less piling And it turned out as we had advised, and they saved a lot of money. Another problem that we see that I touched on previously is that designers may have a goal of using a smaller number of high capacity piling instead of a larger number of moderate capacity piling. And they may think it's more efficient, they'll have fewer pile, it'll cost less money. However, what they're not considering is that this can result in the requirement for a much larger pile hammer. And if you got a much larger hammer, you have to have bigger leads. If you got a bigger hammer and bigger leads, you're going to need a bigger crane. So the contractor may not own that equipment. So they may have to inflate their bids to cover rental costs, and their bids would be lower if it was equipment that they owned that they could use for this pile installation. Or they simply don't bid on the project, and you have a smaller pool of bidders, which inherently would increase the pricing of these jobs over time. Another mistake that we see designers make is thinking that a pile will, quote, refuse in a hard subsurface layer, but that layer doesn't really exist. It's not hard or dense. Merely the SPT blow counts were inflated due to the presence of gravel or cobbles, not really accounting for the limitations of their investigation methodology. To address that, we've been doing seismic refraction profiles to help better correlate anticipated pile penetration depths. You can check out a video here. This is a short version. Or here is the long version, kind of show you some case histories of what we've done. Another thing we see is that designers are putting way too much capacity up to the full structural capacity on the piling for the required geotechnical capacity. And they're not realizing that to drive to a certain stress, which may be your maximum allowable stress, you have additional stresses from the impact of the pile hammer. So let's say your pile's designed to have 30 KSI. If you take the load divided by the cross-sectional area, you could easily have 12 to 15 KSI in driving stresses. So for most piling that are, say, 50 KSI yield strength, you're allowed 90% of that for driving stresses, so 45 KSI. So if you have designers that, based on the load divided by the cross-sectional area, are at or above 45 KSI, there's no way you could get it into the ground and not exceed the allowable stresses. I mean, you simply can't wish a pile into the ground. At extreme, and I've seen this a number of times, but on one particular job, the requirement was for HP 10 by 42 piling driven to bedrock. Depths were typically 50 to 60 feet below grade, and the designer required the pile to be driven to 620 kips. And the contractor was supposed to use a formula to calculate the set and stroke. So in this case, if you take the required 620 kips and divide it by the cross-sectional area of an HP 10 by 42 pile, you're at 50 KSI. So you're 5 KSI over your allowable driving stresses, and you haven't accounted for even 1 KSI of driving stress. So it's an impossible situation. And to make things worse, when you have pile that have very little capacity in side friction and almost all the capacity in end bearing on a hard rock layer, you can quite easily double your input stresses at the top of the pile at the base of the pile. So you could easily have pile damage at the base and not even realize it. So on this project, as I mentioned, the contractor was supposed to verify his installation using a formula, and they called me and told me what was happening. They suspected they were damaging the pile, and they told me some anecdotes which convinced me that they had damaged the pile. For example, hitting one pile and blow by blow a different pile was moving at the same time. That's usually an indication that pile are broken and they're on top of the bedrock contact and they're intermingling with each other. So they had me come out and do PDA testing, and I verified that yes, in fact, they had broken the piling. And it was because they were told to adhere to a pile verification requirement that virtually guaranteed that the pile would be damaged. And actually, I called the designer and tried to explain this to him, and it was like I was speaking Greek to him. He just had he was not receptive to what I was trying to explain to him at all. And this is another problem. Actually, this wasn't on my list, but it just occurred to me. There tends to be, in addition to the silo mentality, a type of overconfidence because you think you know a subject really well, and you fail to consider the input from other people, whether they're degree professionals, whether they're testing consultants, whether they're the contractor. And there's many instances where if the designer had reached out to a friendly contractor, or maybe one they routinely work with on design build projects, and say, hey, what do you think about this? Have you installed a pile of this type, this size, this capacity? What hammer did you use? Just get some feedback, and that seldom happens. So another thing that we see is not factoring in the potential for time-dependent pile capacity increases. Typically, the initial drive capacity is much less than what it will be, say, a few hours or a few days later. Unfortunately, the static capacity design is typically based on the long-term capacity that would be achieved for that pile in that given soil profile. As a result, many piles have increased pile installation depths to reach capacity on initial drive, instead of simply planning for and performing PDA restrike testing after an appropriate waiting period to take advantage of these time-dependent effects. Another thing that we see, and I touched on it earlier, is specifying the wrong pile verification method relative to AASHTO LRFD guidelines. For example, there may be instances where PDA testing should be used to reduce the risk of pile damage, again, similar to the example I gave, particularly for short pile driven to hard rock. Instead, we often see wave equation analysis required or driving formula required, as the designer correctly has little concern about reaching required capacity. But the problem is they're not thinking about the potential and the high potential of pile overstress and damage. That should be their primary concern. If you have a hard rock layer that's fairly shallow, you're going to get capacity. So if you're not doing PDA testing where you can actually monitor the stresses and you can kind of get the fuel settings set for the contractor on the hammer, and so you're just delivering the bare minimum energy to achieve the required capacity, there's instances where I'm leery of even doing the PDA in those circumstances, and we'll have the contractor shut the fuel off, and we'll often get capacity with just a dead blow of the hammer ram, where they just trip it without fuel. So that tells you that if you're trying to achieve a certain pile set and stroke on hard rock that's shallow, chances are you're going to damage the piling. So again, in these situations, wave equation is not a good tool. It's very hard to accurately predict the stresses in this scenario. And again, PDA testing would provide much better protection for determining the pile installation requirements that would avoid pile overstress and damage. And here's another one I touched on earlier. The designer is not collecting and reviewing information on how the pile installation went relative to the design so that they can improve on their future designs. I just don't understand the lack of curiosity. I think maybe people are busy and they've got their tasks, but they need to step back and see the big picture here. And again, as we touched on earlier, one of the top issues is designers not going into the field to watch pile driving installation and associated PDA testing. It would be very valuable experience, and they may internalize that, or they should internalize that if they get enough experience, and end up with far more practical designs for their pile supported bridge projects going forward. If you find these topics interesting, please like, subscribe, and comment. If you have any questions, drop it in the comments. Thanks for watching, and please stay tuned for future videos. I'm going to cover a variety of deep foundation testing and geotechnically related topics, so stay tuned.